Hi friend, welcome again. Today we will discuss about common-emitter amplifier. In our previous lecture we have discussed about the common base amplifier. Now it's time to discuss about common-emitter amplifier. So see here, emitter terminal is grounded and a fixed DC input is supplied to the collector and RC is connected across the collector terminal while input is provided at the base and VE the input fixed DC input to the base emitter to fix the quiescent point or operating point of this transistor. And this is representing the voltage across collector and emitter. VCE, IC is the current through the collector, IB is base current and IE is emitter current. Now this circuit can be drawn in another form also. Here I have simplified this circuit in another way also, and we will measure our output at the collector with respect to the ground. This is our V output measured with respect to the ground. It is also known as voltage across collector. So here we are measuring our output across this terminal. V output positive and negative. This is our positive terminal and this is our negative terminal. So let's start the study of this configuration. In that case, according to Kirchhoff's law, for the collector emitter terminal, VCC minus ICRC minus VCE is equal to 0. So VCE is equal to VCC minus ICRC. Now VCE is equal to VC, so VC is equal to VCE is equal to VCC minus ICRC. So V output can be written as VCC minus ICRC. Now we are using our received input signal which needs to be amplified at the place of input. So in case of DC, case of AC input, we can write our equation V output equals to change in output voltage is equal to change in VCC, and we know that VCC is a fixed DC input, so that's why here change will be 0 minus change in collector current IC RC. So our output change will be equal to minus IC time of RC, and for input we can write down change in V input is equal to change in base current into R input. From current gain of common emitter amplifier, we know that beta AC is equal to change in collector current upon change in base current. So the output is minus time of ICRC. Output is minus time of ICRC and our input is del time of IB, our input. So next point, we are going to discuss about the current gain of this amplifier. So let beta, we know that beta is equal to alpha upon 1 minus alpha. Just we are going to compare between common base amplifier and common emitter amplifier. Let alpha is equal to 0.98, so that's why beta will be equal to 0.98 upon 1 minus 0.98. It can be also written as 0.98 upon 0.02, so the value can be written as 98 by 2, that will be equal to 49. So the current gain in case of common emitter amplifier is higher than the common base amplifier. So from here we can conclude that for the same transistor, current gain in common emitter configuration is higher than the common base configuration. Our next point to discuss about now, voltage gain. So the voltage gain in common emitter amplifier, it is defined as the ratio between change in output voltage to corresponding change in input voltage. So current gain AV is equal to change in V output upon change in V input. From previous page, we can write down that change in output is minus change in collector current and RC, and change in input is change in base current into input resistance. So it can be written as AV equal to minus del IC RC upon change in base current time of R input. So voltage gain is equal to minus time of beta RC upon R input. Here the voltage gain is negative, so minus sign or negative sign so that output will be in 180-degree phase difference with input. Our mathematical calculation is showing that the output will be 180-degree phase difference with the input. Now see with the working of the transistor. Suppose we are providing input in this way. So the output will be when we are considering positive half, in case of positive half, this base emitter junction will be more forward. When it will be more forward, in that case value of collector current will be high, and due to high collector current value, its output will be very less. That's mean at 180 degree. And when we are providing negative, in that case it will be reverse bias, so that's why IC will be decreased, so there will be change, much more change in the output. So this is the input and output graph for the common emitter amplifier. Here the phase difference between V input and V output is of 180 degree. So our gain is minus beta time of collector resistance upon input resistance. We will consider a new factor that is known as transconductance. We know about conductance. Conductance is the ratio between current to the voltage. But here the word transconductance, it's mean the transfer of conductance. We are talking about transfer of conductance. In case of transfer of conductance, there will be output current and input voltage. So transconductance is represented as change in collector current upon change in input voltage. And we know that our voltage gain AV is equal to V output upon V input, and V output can be written as minus ICRC upon V input. So that's why its value of voltage gain is equal to minus GM RC, where GM is representing transconductance. Now we have discussed about the current gain, voltage gain, and voltage gain in the term of current gain and also in the term of transconductance. Now our next point is to discuss about the power gain of this common emitter amplifier. So our next point is voltage gain. And power gain. So power gain is the ratio between output power to the input power. So power gain AP is equal to output power upon input power, and from here we can write down output power and input power. Then output power will be equal to change in IC into change in V output upon input power change in base current to the change in V input. So from here we can write down beta time of voltage gain, V output change in V output to the change in V input. So it is beta time of AV. It can be also written as power gain is equal to minus beta square DC AC into RC upon R input. Now, the energy for the higher AC power output is supplied by the DC battery, so it appears from the relation VCE equal to VCC minus IC RC. The gain of the amplifier can be increased indefinitely by increasing load resistance RC. This is not so because in this case VCE decreases, and when VCE become less than VBE, both the junction will be forward. In this case the transistor in this situation is saturation stage and can no longer be used as an amplifier, because when we are increasing the value, in that case VCE, when VCE became to VBE, so both will be forward. So transistor will work in saturation region. So it can be used as an amplifier in this case. So we have finished the discussion about common emitter amplifier. In next lecture we will discuss about the transistor as an amplifier with voltage divider biasing. Thanks.